Hello everyone. Today we are going to study or understand the chemical reactions of potassium dichromate. Now, preparation of potassium dichromate has already been explained in the previous video. Please refer that and do try to understand how from iron chromate ore we are preparing potassium dichromate. A wonderful question asked in board examination. Another thing, potassium dichromate works best in acidic medium, especially with sulfuric acid. So a general equation of potassium dichromate in the acidic medium has been explained perfectly in the previous video. Please make sure you go through that before beginning this reaction. Now, potassium dichromate is a wonderful oxidizing agent and works best in acidic medium. From the previous video, we can expert about the reaction, okay, of dichromate ions and acidic medium. One thing to notice, and please make sure you make a note of it, that potassium dichromate or dichromate ions in the acidic medium give out chromium ions with the oxidation state +3. In the other sense, dichromates change into metallic chromium. So that is the beauty of acidic medium. Acidic mediums generally release out the metallic ions. In the case of potassium permanganate as well, manganese permanganate ions in the acidic medium release out manganese metallic ions. Okay, so that way we can remember it. Do make sure to go through the video and understand this particular reaction. Today, we are going to understand the oxidation of potassium iodide to iodine using acidic potassium dichromate. Now, potassium iodide is nothing but two ions combined. One is K plus and another one is I minus. Okay, so we are going to convert the I minus ions into iodine. If you look closely, iodine happens to be a molecule, and all the halogens basically are diatomic gases. Some of them are not, but yes, most of them are diatomic. And being diatomic molecule means what? Two iodine atoms come together, share out their electrons, up their valencies, and stabilize themselves. That's why you don't find any charge on iodine molecule. But right over here in the reactant side, in the potassium iodide, we can see a -1 charge, meaning we are turning an ion into a molecule. Two atoms of iodines are required, but we here have only one atom of iodide. So we are going to take two atoms of iodide ions and convert them to iodine. If you look closely, iodine molecule has no charge, but iodide has one minus, and we have two iodides. So two negative charges on the reactant side, but no charge on the product side. So we somehow need to eliminate the two minus charge. Best way to eliminate them is to remove them in the form of electrons. So two iodide ions being converted to iodine and removal of electrons. If you see over here, there is a loss of electron. Whenever we write electrons in the product side, it's called loss of electron. Whenever we write electrons in the reactant side, we call it gain of electron. Make sure to read this again. We are looking at oxidation of iodide to iodine. Oxidation itself means loss of electron, and here we are even proving it. Reduction, on the other hand, is gain of electron. Okay, we are going to use this equation with our general equation of potassium dichromate in acidic medium. So it's like a mathematical equation, you have equation number 1, you have equation number 2, you need to equate them, tally them, cancel anything that's common, and thereby you get your answer. If you notice carefully, in chemical reactions, we do not generally mention electrons in the final reaction. We try to avoid writing electrons or specifying electrons in our reaction. But you can see in the first reaction, we have 6 electrons And in the second reaction, we have 2 electrons. We need to somehow convert these 2 electrons into 6 so that 6 and 6 can cancel. Best way to do it is to multiply the entire equation by 3. Why not only the electrons? Because we can't locate and localize only one part of the equation and multiply it with a number. If we wish to multiply a particular part of the equation with a number, we need to do that for the entire equation. So the final second equation we get is this. Notice carefully, 6 electron on the product side, 6 electron on the reactant side. We know how math works. We are going to eliminate them one by one. So write down both equation 1 and 2, one below the other. Tally them up. Okay, tally them up. So all the reactants on the left-hand side of the arrow, all the products on the right-hand side of the arrow. Okay, what do we find common? We find 6 electrons common, and we eliminate them. Now we are left with the final equation. You can leave your equation right here, and I promise you would be scoring complete marks. But some invigilators, some moderators do prefer the compound forms of these reactants and products. So let's try to even look at the compound forms. Okay. We have this particular equation from the previous slide, and we are going to look at the compound forms of these equations. Dichromate ion is nothing but potassium dichromate. Proton is nothing but sulfuric medium. Iodide is potassium iodide. Cr3 plus is dichromium sulfate. Water remains as water. Iodine is iodine. Now, what is happening over here? Basically, we are writing all the ionic forms into compoundic forms in order to satisfy the equation. If you leave it in the ionic form, I'm definitely sure that you would be gaining marks. Some teachers prefer compoundic forms, and it's okay to remember. It's not that difficult. Okay, so can you see over here, the chromium is going to combine with sulfate to give you dichromium sulfate. One might ask how these subscripts are coming into picture. Notice, chromium state we have taken is +3, meaning we need to write 3 below it. Sulfate has a charge of -2. While allocating the numbers in a formula, we do not put plus and minus, okay? Cross multiply. You remain with Cr2SO4 thrice. Okay, dichromium sulfate. Pay attention to one more aspect. If you notice, we have 14 protons over here. And we have H2SO4, meaning the formula itself has 2 in it. So what do? We multiply that 2 with 7 and get 14 protons. Next, we are going to take 6 iodides combined with 6 potassium to give 6 Ki. Here, we have almost completed the reaction. But if you look closely, some potassiums have not been utilized and some sulfates have not been utilized. So there are totally 7 sulfates, correct? Of these 7 sulfates, 3 sulfates have been taken up by chromium to form dichromium sulfate. Okay, whereas 4 sulfates are remaining. Along with them, even 8 potassiums are remaining, and we do not find them in the product. So what do? We need to understand potassium has a charge of 1, sulfate has a charge of 2. You cross multiply, you're bound to get K2SO4, meaning potassium sulfate happens in the ratio 2 potassiums into 1 sulfate. How many sulfates do we have? We have 4 sulfates with us. So 4 sulfates, 4 twos are 8 potassium. Do we have 8 potassiums? Yes, we do have 8 potassiums. So 4 sulfate, 8 potassiums. Okay. This is where you can end your equation. If you leave them in the previous slide form, no problem. If you take them ahead, you are actually, eliminating any chance of a moderator to deduct your marks. Okay, so that makes it easy. Final equation boils down to potassium dichromate reacting with sulfuric acid and iodide, potassium iodide, to give dichromium sulfate, water, iodine, and potassium sulfate. Best part to know when the reaction ends is potassium dichromate reddish orange in color. So initially when you start the reaction, you might find a reddish orange solution. And once you have added all the reactants, let it react for 2 minutes. You're going to see brown fumes or brown solution color. This is indicating the elimination of iodine from the solution. Okay. So once you understand that the color is turning brown, meaning your reaction is complete, and oxidation of potassium iodide to iodine has successfully taken place. For understanding better on how these electron exchanges and all are happening, make sure you go through the video of equation of potassium dichromate in acidic medium. That video is pretty helpful, and it would be actually logical to refer to that video first and then to this video. Pause the video over here, go through this again, recap, try to write the equation formats on your own without looking, and try to compare whether you have understood or not. If not, I always suggest that watch this at a pretty slow speed, understand what is happening, and if you have understood and you want a recap, just make sure to put this video on 2x, repeat it, and get your doubts cleared. The second equation we have is oxidation of hydrogen sulfide to sulfur. Hydrogen sulfide is what? H2S to sulfur. Now, H2S can also be written as, when we split H2S, we are actually getting 2 hydrogens and S2 minus. We know one thing, that of hydrogen sulfide, only sulfide is capable of converting into sulfur. Hydrogen does not play any role. Correct? So you can see sulfide S2 minus turning to sulfur, monoatomic sulfur. This sulfide has 2 negative charges along with it, whereas this sulfur is neutral. That means we need to eliminate these 2 charges in order to get our product. Best way, lose them out of the equation. Loss of electrons over here indicates that the reaction is oxidation. Okay, we are repeating the same steps. Consider the equation of dichromate in acidic medium. Put down your equation that you have got from the question, that is hydrogen sulfide to sulfur. Pay attention on the electrons. We do not want electrons in our final equation. Initial equation or first equation 6 electrons. Then we have 2 electrons. We need to equate these two. So we are going to multiply the entire equation with 3. When we multiply it by 3, we finally get 6 electrons even on the second equation. So here in the reactant side, we have 6 electron, product side 6 electron cancels out, thereby eliminating involvement of electrons totally from the reaction. Last step would be to tally out both the equations, reactants on one side, products on one side. Okay, what do? We do the same thing. We are going to eliminate the same number of electrons. Thereby, we are left with the actual equation. You leave it over here, all good. Nobody is going to blame you for anything. But if you take it to the compounding form, then even the moderator can't deduce your marks. Compounding form is the same as the previous one. Our dichromate ions, they turn into potassium dichromate. Hydrogen ions turn into sulfuric acid, sulfide ions, hydrogen sulfide. Chromium ions to dichromium sulfate. Water remains as water, sulfur remains as sulfur. Here, one thing that clicks is that we have 14H plus, but we have two compounds occupying hydrogen. So we need to properly split 14 hydrogens into these two compounds. Best part being that for hydrogen sulfide, already there is a predetermined coefficient. So we need to put 3 over here. There is no other alternative. 3 2s are 6, meaning hydrogen sulfide occupies 6 electrons. 14 minus 6, 8 hydrogens. So we make 8 hydrogens in sulfuric acid. 4 2s are 8. So we need to split it accordingly. We can't vary the number of protons, otherwise the first equation will completely collapse. Okay. Last thing we are left, there is no potassium in the product. Excess sulfate can't be seen. So how many excess sulfates do we see? We see only one excess sulfate. That sulfate combines with 2 potassium to give potassium sulfate, thereby concluding your reaction completely. How do we know that the reaction is completed? When you are mixing potassium dichromate with hydrogen sulfide under acidic conditions, initially it would show orangish red or deep orange color, and later after 2 to 3 minutes of reaction in heat, we'll understand that the color of the solution changes to green and some effervescence can be seen. So this green color itself indicates that sulfur has been produced and products have all been formed. This is how we carry out the oxidation of potassium iodide to iodine and hydrogen sulfide to sulfur in the acidic medium of potassium dichromate. Refer to the other videos of potassium dichromate to get a clear picture on how things are working. Meet you next time. Signing off. Bye.